Okay, what's up, guys? Let me give it a second here to get everything set up. Um, all right. So, give about 20 seconds here for the in people or in people who like to watch it live to show up. Let's see. Well, they'll come when they come. They can always look at this later. Anyways, I want to start out class today just really quick with just a little bit about an announcement I sent out this morning. So I played around with this a little bit. If you didn't notice, there was no lecture on Monday. Or more accurately, if you happened to be there live in attendance, there was part of a lecture that was canceled midway through. My wife was at an appointment that ran a little bit long, and I had my son with me. I tried to give a lecture while holding a baby, and it was predictably a bad idea. So I figured I'd record it the next day. Then I recorded it the next day, but forgot to turn on my mic. So we had to do something about it. We had to figure out a way to fix this, and instead of just giving double long lectures and making everyone have to do more material in less time, I figured something that might be nicer, and I think you'll probably like, is modifying the schedule a little bit with this upcoming exam and spring break. So, in particular, the changes are already all updated in the syllabus and the due dates for assignments and everything like that in the course schedule. But in particular, in this announcement I sent out, I have the old schedule compared to the new schedule with color-coded highlighting of the changes that have gone on. What we're going to do, since we basically impromptu canceled class on Monday, is we're just going to do Monday's material today. Then we'll do what we were going to do on Wednesday, on Friday, and so on. We'll push everything back a day. And then I'll move the homeworks back by a class as well. And the exam, because we don't necessarily want to move that back by a class, you guys should at least have the same amount of time. I've moved that to start on Thursday now instead of Wednesday, and have it be due on the Monday after spring break. So not at 8 a.m. or something, but by the end of the day. So you still get 3 full days, 3 full non-break days to complete all of this. But you now also can use spring break if you want. Hopefully that'll make things a little bit easier for you. And all the changes should be to your benefit. So if you have any questions, please let me know. Shoot me an email. But I just thought I'd touch on that real quick. With nothing more to say about that, let's get back to the material. Okay, so we are gonna get a little bit into some of the real nitty gritty of analysis today, and that's pretty exciting. So we're gonna go back and look at Cauchy's theorem a little bit more closely. We're gonna do some good classic epsilon delta arguments, some fun arguments, and we're gonna kind of tie a nice little bow on Cauchy's theorem. So what the story so far is, just to refresh everyone's memory, is that in 2.1 we got a preliminary version of Cauchy's theorem. We went at it with a proof motivated by Green's theorem. We didn't prove Green's theorem since that's kind of a classic like Calc 3, Calc 2 theorem, but it might not seem satisfying to you to rely on this other theorem so much. Also, we can kind of change the assumptions a little bit and prove it without needing it. So we're gonna go do that today. But in section 2.1, we also got this path independence theorem. And I wanted to clarify briefly a few things about the path independence theorem, because I think people may have developed some slightly inaccurate ideas of what it says. In particular, the path independence theorem says that if f is a continuous ooh, that's a little bit too much of a highlight. Let's see. Yeah, way too much of a highlight right there. Let's drop that down. If f is a continuous function on an open connected set G contained in the complex plane, then the following are equivalent. That is, it's not the case that you get all three of these for every continuous function on an open connected set. That's not true. What you get is that all three of these things are equivalent, right? So if you have path independence, then you automatically get that integrals about closed curves are 0. Similarly, you automatically get a global antiderivative for f on g. If you have any one of the other ones, then you get the other ones, and so on and so on. These guys are equivalent. Okay, fair enough. So, what then is Cauchy's theorem all about? What are we proving today? What is the real thrust of the rest of it? Well, it's Cauchy's theorem tells us, and let's jump over to a closer look at Cauchy's theorem. We'll start out with Cauchy's theorem for a rectangle. The version of Cauchy's theorem you've seen thus far was a little bit more general than this thing we're going to start out with. But basically, Cauchy's theorem tells us that analytic functions, or functions that are analytic and easiest way to say it, functions that are analytic have a 0 contour integral about a closed curve in their region of analyticity, where the interior of the closed curve is contained in the region of analyticity as well. That is, if you've got a closed curve lying entirely in an open connected set where g is analytic, or the function is analytic, then if you integrate around it, you get 0. So what Cauchy's theorem is telling us in relation to something like the path independence theorem is that one way to get all of these nice equivalent facts about continuous functions on an open connected set, all these nice things that you get are automatically equivalent if you have one of them, you can get one of them with analyticity. So being complex differentiable gives us access to that path independence theorem. Okay, so Cauchy's theorem for a rectangle. Let's start out and let's prove this bad boy. So we're going to suppose that R is a rectangular path with sides parallel to the axes, just kind of like a very basic path. And we'll suppose that f is a function that is defined and analytic on an open set G containing R and its interior. What we're going to claim is that the contour integral of f about this rectangle is 0. Okay, doesn't seem too crazy. Let's do a proof here. Let's get really into it. So, kind of a nice thing maybe before I actually get into this piece might be to sketch out what we're looking at, the context here. So let's start out by drawing some axes. Fair enough. Switch to a different color, and I'll make a rectangle real quick. We've got our rectangle here. Let's call it R. Okay, then we've got some open set G containing R. Okay, and this is a place where f is defined and analytic. This contains R and the interior of R. That means that R is entirely inside of G. All right, fair enough. And let's start out by defining a few nice quantities. So in particular, and we're gonna this picture will get kind of busy sort of fast. Let's call the length of the diagonal here. Let's call that say like delta. Big capital delta, looks like a triangle, right? And then let's call the distance around the outside of this rectangle, how long this path is, the perimeter of the rectangle, obviously. Let's call that P for the perimeter. Okay, now we've got some nice quantities, and let's begin our proof. This picture will save me having to necessarily write like, let P be the perimeter of R, which no one likes to watch me slowly write things on the screen. So the first thing we're going to do is we're going to divide R into 4 subrectangles that are congruent. And let's call these guys, I don't know. RA, RB, B, R, C, R, oops, R, D. How about? Okay, so what does this picture look like? Let's get in here. Let's kind of draw this out. So we're gonna break this into, 4 quadrants basically. Here are our 4 subrectangles, right? We've got these little chunks. All right, and this is kind of a laborious picture to draw. There we go. Okay, so we've got our little chunks right here, and as you can see, I didn't actually draw that diagonal or these chunks too well. That should go right through the middle. Dang it. Close enough. Close enough. Anyways, um, keep my colors consistent. Then, just using the additivity of a contour integral, notice something nice. I'm going to claim that the integral about r of f is equal to the sum of the integrals about each of these pieces. So the integral about RA plus the integral about RB plus the integral about RC and plus the contour integral about RD of f. And why is this true? Well, to see it, kind of go back over here and notice that as you're going around each one of these guys, right? If we add all these up, so just throw in some arrows real quick so we can see it, you're going to get some really nice cancellation. Okay. In particular, notice these guys just in opposite directions, right there, right? Those guys are just going in opposite directions. So when I integrate one way, then when I go back and integrate the other way, it'll just give me the negative of what I got. And so when you add them together, you'll get 0. And so all that's left, the only parts that don't cancel out, are going all the way around the outside, right? These outside edges of our contour integrals don't get canceled out by the other the other squares contour integrals. Hence, we can say that the contour integral about the big square is equal to the sum of the contour integrals about the little squares, because we get this cancellation. So that's kind of a nice little trick right there. All right, so let's use a great inequality to give ourselves a bit of an upper bound. How this works is we're going to say, so it is true by the triangle inequality that, and once again, it's just going to be exactly the same thing. The integral of f about r is less than or equal to, and I'll skip a step here just for convenience. Naturally, of course, if you throw modulus bars around on either side, they're still equal, but if I break it up across the sum using the triangle inequality, I get that it's less than or equal to. So this will be the integral about a of f in modulus, of course, plus in modulus the integral, and this is not about a, sorry, about ra, rb of f, and so on, right, with rc and rd. Okay, so what can we do with this? Well, hence, for some subrectangle, call it R1, it must be true that 1/4 the modulus of the integral about r of f is less than or equal to the integral about r1 of f in modulus, of course. So what this is saying is just that if you have a sum of 4 distinct things and it's bigger than something, then at least one of those things must be bigger than a fourth of it. If they were all smaller than a fourth of it, then you couldn't add four things. If all four things are smaller than a fourth of this thing right here, then you couldn't add all of them up and get something bigger, right? Okay, that's not too weird, I don't think. But hey, look at what this tells us. If I multiply by 4 on both sides, I now have an upper bound in terms of this subrectangle. Okay, cool, right on. So kind of visually, we're getting something like, maybe this right here is R1. Maybe that's what happens to be R1. At least one of these guys, we have this subrectangle where when you're integrating around it, you're going to get something that's bigger than a fourth of integrating around the whole thing. Okay, fair enough. Fair enough. Nothing too weird. All right. We can also get some estimates on things like the perimeter, and I know it's kind of covered up now, but the length of the diagonal for the subrectangle as well. Okay. So, additionally, the perimeter of R1 is 1/2 the perimeter of R, which is P, right? So 1/2 P, right? And the diagonal is 1/2 the diagonal of R. All right. So let's call this perimeter of R1. Let's call this P1. Why not? And let's call the diagonal of R1. Let's call this big delta 1. Okay. There we go. So notice we can do a nice trick. Now we've got ourselves this new rectangle, and we could just pretend, since we still have a rectangle that is lying entirely inside of G, since the subrectangle lies inside of R and it's, the interior of R or on the boundary of R, right? Okay, fair enough. We're back in the same context we started in, and we could just repeat this exact process over again. Okay, so now repeat this process for R1 to obtain, let's call it R2. Same thing we did as before, but now we're going to get a subinterval of R1, or a sub rectangle of R1, and we'll just keep going. And that looks like I said and soon. I mean, and so on. Okay, okay. We get that. Well, we get a couple of things out of this. We can just basically do exactly the same things you're doing right here, and the same thing with the perimeter and the diagonal. Let's write these things out. So 1, okay, 1, we'll get that the integral about Rn of f in modulus is greater than or equal to 1/4 of, did I say, should that be 1/4? That should be 1. Or no, sorry, that's fine. I almost said perimeter. Okay. Yeah, no, that's this should be 1/4. Sorry. This is just exactly what we did right here. The 1/4 business. This thing will be bigger than 1/4 the modulus of the integral about Rn minus 1 of f. And that's going to be greater than, 1/4 squared of the modulus of the integral about Rn minus 2 of f, and so on, all the way down to 1/4 to the n times the modulus of the contour integral about R of f. Huh. All right, how about that? That's not too bad. And from here, we can do the same thing with the perimeter and the diagonal. Okay, so the perimeter of the nth subrectangle is 1/2 2 to the n times p, the perimeter of the original rectangle, or just maybe more simply, that's p over 2 to the n. And similarly with the diagonal, the length of the diagonal of the nth rectangle is 1 over 2 to the n times the diagonal of the original rectangle. That's just the diagonal of the original rectangle over 2 to the n. Okay. All right. Nothing too weird so far. Now what we're going to do, since we've kind of started to build a lot of little pieces in here. So, what color should I use? The idea, I guess I'll use purple. The idea of what we're going to do next is pretty. Here, let me draw this square, and then you'll see it. So we're grabbing little sub-rectangles. Maybe the next sub-rectangle's right in here, and then we've got one maybe over here. Maybe the next one's down in that corner, and the next one's over there, and so on, right? If you notice, it's going to kind of go down to 0 or not to 0, but the size of the rectangles shrinks down to nothing, right? Does that make sense? The size of the rectangles goes to 0, and it sort of seems like they must shrink in on a single point. So we'll make a sequence, and we'll show that it does go there. So you could take any point on each rectangle, and since the rectangles get small, no matter what point on the rectangles you have, it will get eventually close to this point. But for convenience, let's just take like the top left corners. So that'll be like this point, and then that point, and then this point, and then that point, then like this point and that point. And it just spirals down into it, right? Okay, so let's write this out. Take Zn to be, let's do the top left corner of the nth rectangle. Then, if m is greater than or equal to n, in modulus, the Zn minus Zm, this is the distance from Zn to Zm, this guy will be less than or equal to, I claim, the length of the nth diagonal. Why is that? Well, because anything for m greater than n, you're inside of Rn, the nth rectangle. And notice the furthest away in a rectangle 2 points can be from each other is on the opposite end of the diagonal. That is, this is the hypotenuse of a triangle, and so that's that's longer than either of the legs, right? So that's the furthest you can be away. Okay, so that's well, we already know a formula for that, right? That is delta over 2 to the n. Okay, fair enough. Notice we've got a sequence of points that all, as you take this n to be very large, this gets close to 0, right? So you've got a sequence of points that gets close together. We talked about this before. This is a Cauchy sequence. So the sequence Zn is a Cauchy sequence. And by completeness, we get that it approaches some point, let's call it W naught, in the complex plane. Okay, so we got this sequence of points, and it's going to converge down to something, some fixed point here, W naught in C. All right, now, if Z is any point in the nth rectangle, or actually here, let me back this up a second. Let's do it like this. Okay. So we've got, so Zn is a Cauchy sequence. We're going down to this point in the complex plane. And so there's this limiting point somewhere down in here. All right. Now what we want to do is we want to use the fact that f is analytic on G. And so it's definitely going to be analytic at this point. What we'll do with this is we'll use this to create an upper bound for this piece right here. If we can show that we can make this upper bound as small as we want, then we can show that this integral has to be equal to 0. Okay, so let's kind of sketch what this looks like. We've got a Cauchy sequence converging to some point here. Now, if z is any point in the nth rectangle, then notice z minus w naught has to be less than or equal to delta over 2 to the n, right? Okay. Nothing too weird. We've basically repeated the same argument we just had right here. Because w naught is, once again, it's definitely in all of the rectangles because it's, each subrectangle is inside of the next one, right? So this is just basically exactly repeating the piece we did right up here. Okay, so we've got that nice little fact. So let's use differentiability. Using the differentiability of f at w naught, we have that for any epsilon greater than 0, so for any positive real number, there exists a delta greater than 0 such that, and this is what it means to have a derivative, well, f of z minus f of w naught over z minus w naught minus f prime of w naught is less than epsilon. That is, there is a value here, this f prime of w naught, such that as you take the limit of whatever this piece right here, this difference quotient, you get close to it. What does it mean to get close to it? It means that for all epsilon greater than 0, you can make this close whenever z minus w naught is less than delta. So if n is large enough, that is, we already know that z minus w naught is less than or equal to delta over 2 to the n. So if n is large enough that delta over 2 to the n is less than delta, capital delta, small delta there, then, and now we're going to jump into something that will deliver us a large string of inequalities in a moment. So what we get here, then what we have is that, so just multiply everything in here by z minus w naught, or get like a common denominator, right? And then use the fact that modulus of a fraction is equal to the fraction of the moduli, provided the bottom is defined, and then multiply that over. So we'll get, I'll write it out and you'll see it immediately, basic algebra, f of z minus f of w naught minus z minus w naught, that quantity times f prime of w naught. This thing, actually, let me move this down very slightly so we don't get too crowded here. Okay. This is less than or equal to epsilon times the modulus of z minus w naught. Can you see how we got that from here? We just got a common denominator, split the modulus up over the this absolute value bar up over the top and the bottom, and multiplied over. And hey, what do you know? This will be less than or equal to by this little business with z minus w naught being less than delta, right? This will be less than or equal to epsilon delta over 2 to the n. Or rather, that's a z minus w naught less than or equal to that, right? Okay, so there you go. There you go. Now we're up to that. So let's go back and pull this this piece from down here, right? This guy is greater than or equal to, and you go all the way down the chain to 1 over 4 to the n modulus integral about r of f. Let's multiply both sides by 4 to the n, and let's start right there. So here's the fun trick. So here's the big business. We're going to go about r with f in absolute value right there, right? This is less than or equal to 4 to the n, and we're going about r, the nth rectangle, right? Okay, and now I'm going to do something. I'm just going to write it, and you're going to probably be like, that makes no sense to me. But when you see it, you'll be like, that is the dumbest trick I've ever seen, and it's amazing that it works. So integral around the nth rectangle, f of z dz, I'm going to write in my dz's now just for convenience, minus f of w naught, and integral right here of 1 dz, and I'll do this around the nth rectangle, minus f prime of w naught, integral around the nth rectangle, z minus w naught dz, and of course all of that is in modulus. Why on earth am I allowed to do this? Well, this guy right here and this guy right here, I'm going to claim since 1 and z minus w naught have antiderivatives everywhere, these integrals are 0 by the path independence theorem. Hence why we brought it up at the beginning of class today. By the path independence theorem, these guys are all 0. So look, a thing times 0, a thing times 0, I've added 0. That's all I did. I added 0. Isn't that, like that wonderful, exciting, dumb kind of trick that we all just love? Okay, so I added 0. What am I going to do now? I think you can all probably see what's about to happen. Well, I assume at least we can just take this all and put it together. Everything's still in absolute value bars. I'll bring all of these pieces together. I'll have f of z minus f of w naught, bring it, inside the integral and so on, minus f prime of w naught, z minus w naught, and all of this dz, and it's all still inside those bars. And now, hey, wouldn't you know it, I guess I should write this step. It's less than or equal to 4 to the n, and notice since I've got the modulus of an integral, I can bring that modulus on inside at the cost of a less than or equal to 4 to the n integral about the nth rectangle of the modulus of f of z minus f of w naught minus f prime of w naught, z minus w naught. So that thing, dz, maybe I should put like a modulus around dz to like be careful or something. And hey, now we can do the thing we really want to. Look, I've got this big old absolute value right here that I just bounded right up here by epsilon delta over 2 to the n. So 4 to the n integral about r to the n. And actually, I'm going to use this bounding theorem, if you guys remember this one, where you can bound, if you have a function that's bounded by something, then you can take the contour integral and bound it by that bound times the length of the curve, right? Well, what's the length of the curve? Well, it's the perimeter of the nth rectangle. So that's going to be the nth rectangle's perimeter, and then epsilon delta over 2 to the n. But hey, what is the nth rectangle's perimeter? Well, that is just going to be, I'll write it like this so I don't run out of room. That is, I'll just put down 4 to the n, and then this is p over 2 to the n, epsilon delta over 2 to the n. And look, bam, 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 I just get epsilon p delta. So epsilon times the perimeter of the rectangle times the length of its diagonal. But since this holds for all epsilon greater than 0, it must be the case that in absolute value, the integral about r of f is equal to 0. That is, this thing, if it's less than every positive number, the only thing that's less than every positive number while being non-negative is 0, right? And so if you have something that's 0, that's the only thing with a unique modulus in C, right? So the integral about r of f is equal to 0. That's the only way you can get out 0 in terms of that absolute value. And bada boom, we just proved it. How about that? That is if we zoom out, that is a pretty beefy looking proof, yeah? It's a long one. All right, fun. So this gets into a little bit more of the fun bread and butter type of analysis proofs involving epsilons and deltas, where you subdivide things, you use analyticity to get bounds on stuff. This is a proof due to, I believe, Gorsat back in the day. And it's cool because it doesn't require us to use Green's theorem. All right. Nor does it require that the derivative of f be continuous. We'll actually use this later on to show that that is automatic, that analytic implies infinitely continuously differentiable, which is very crazy compared to the real case. We didn't have to use anything about the continuity of the derivative, and we'll show later that we actually get that for free. But let's move on from that piece and talk a little bit about Cauchy's theorem for a disk. So Cauchy's theorem for a disk is a little bit more similar to something that we maybe want. We might be more familiar with disks. It might seem hard to imagine how to adapt that that theorem involving squares to something like a disk. Okay. Well, the statement of the theorem, which I guess we should talk about first, is just the obvious analog. It tells us that if we have f from the disk into the complex plane that's analytic on this disk centered at z0 of radius rho contained in the complex plane, then f has antiderivatives on d. That is, there's a function from d into c that's analytic on d and satisfies big F prime of z is little f for all z in the disk. And if gamma is any closed curve in D, then the integral about gamma of f is 0. So from the path independence theorem, which we've already proved, we know that these things are equivalent. So we only have to prove one of them. If we prove the first one, we'll get the second one immediately. So that's what we'll end up doing. Now, I guess since these proofs take so long, I'm going to give an extra credit opportunity right here. So write up a proof of, what is it? Theorem 2.3.2 and send it to me. I'll make this worth, I don't know, let's make this worth 10 points. So half of a homework assignment. And in big, bright red letters, I will ask that you explain all the steps. God, that is the messiest writing right there. Explain all the steps. So the proof is in the book. It's totally fine for you to use the proof in the book. There are a couple of typographical errors, like notational errors, that try to catch them. But the proof in there is fine. You can use that. I guess if you just copy it down directly, you probably won't learn much. but I'll still give you points. Don't do it. I mean, you're still probably learning something, and it would be so little extra effort to understand it. Um, but yeah, just write it up. Go look in the book and kind of let it guide you. See if you can prove it yourself if you want. I'll give you a quick, I guess, proof sketch of what you do, and it's a kind of fun trick. So let's let double angle bracket AB denote the path from A to B formed as, and I'll kind of draw the picture like this. You've got A over here, and you go over, and then you go up to B. That is, you travel along, the real direction. You could also go to the left and then down, or to the left and then up, or to the right and then down, right? But you do it like in this like right angle-y path, right? So this path, we'll call that angle bracket AB. So what we're going to want to try to show, we'll try to show that the function big F of z, defined as the contour integral along this path from z naught to z, where if you recall, z naught in the statement of the theorem is the center of the disk, right? Z naught to z of f of, I don't know, we use some different letter because we have a z right there, zeta, d zeta. Okay, so, or c, I don't know, a tornado looking letter. We'll try to show that this guy is an antiderivative of f on the disk. That is, i.e., we'll show that the limit as w goes to z of f of w minus, oops, I should use big F. F of w minus f of z over w minus z is equal to little f of z. So just this classic definition of the derivative. And how we'll leverage the path independence, or we'll use the path independence lemma, and we'll also use Cauchy's theorem for square. How the heck will we do this? Well, kind of to give you a little bit of the hint that will make it intelligible. Here's sort of the picture, is that you'll have, there's two basic kind of cases that it can occur, and just to sort of make it easy to see, I'll draw them both right now. So right in the center of your disk, you've got z naught, right? And that's in either case. Z naught, okay. And then I'll go into a different color, and let's put, I don't know, let's put like z over here. How about? Actually, I'll write on the other side for that. Otherwise, I'll probably end up going over my path. I'll put z over there or something. Or let me put that one on the other side. Okay, there we go. So when you go from z naught to z, you go over and then you go up. That's that right angle path, right? Okay, over and up. Okay. Now, if I had another point, let's call it W. The point W could be like over here or something. Okay, well then I could take that guy. I could go, just over similarly. And then I could go up. Or maybe the point W happens to be like over here, right? Well, then I could just go over a little bit and then go up. And of course, you can imagine if, these guys were up, down, left, right, something like that. I'm just trying to show you that it doesn't matter if it's like closer or further, and you don't have to make yourself some big confusing situation. Notice you can also go from Z to W. That is, you can go over here and then up. Or in this case, you would go over like this and then up. And hey, wouldn't you notice it? we've suddenly gotten ourselves a little bit of a square right here. And we know that when we go on this guy, we get 0. So we'll use Cauchy's theorem there and say something about the, Cauchy's theorem on a rectangle, and do something with this, this piece, this business right up here, since f is defined in terms of some integrals, right? And if we want to look at the path from z0 to w and the path from z0 to z, which would be evaluating big F of W and big F of Z, right? Then when you compare them, you can put them together in such a way so that you can get this little square, and you'll know that the contour integral about that piece is 0. Hint, when you're subtracting right here, you're actually subtracting some integrals from each other, and you can sort of put things together. So try to do that and see what you get out. You'll be able to use some nice facts to get what you want. And that's the extra credit right there. So without spending too much time on that, it's another kind of fun and involved proof, but it's relatively similar, and you should get some more practice with epsilon delta arguments. I don't want to brutalize you on homework with lots of very involved proofs, mostly because I also don't have time to read 20 multi-page long proofs and provide detailed comments every week. It's a great opportunity for you to get to do that, and if you want to ask questions, let me know. You can also get some extra credit. It's a great idea. So let's look at a few other theorems and see if we can kind of get a bit of an idea of how to deal with other situations, how we can strengthen Cauchy's theorem a little bit. So I won't write out these proofs in full detail. We'll use the book's proofs. They should be good enough. No, they're great. Let's look at lemma 2.3.3, which we want to maybe get rid of the analytic everywhere kind of condition. Maybe there's just a point where it fails. These are things like 1 over z or something, except maybe not quite. A little bit less bad than that one. So let's maybe more like 1 over, I don't know, z squared or something. Who knows? Let's suppose that R is a rectangular path. I'm going to make that a little bit brighter and easier to see. Actually, with sides parallel to the axis, and the f is a function defined on an open set G containing R and its interior, and f is analytic on G. So far, we've got exactly the same conditions as Cauchy's theorem for a rectangle, and now we're going to add the new piece. Except at some fixed point z1 in G, which is not on the path R. Okay, so there's some point not on the path where f fails to be analytic. Suppose that at z1, this fixed point in G where f is not analytic, that's this point that's not on the path R, the function f satisfies the limit as z goes to z1 of z minus c1 of f is 0. Then we're going to claim that we still get the exact same result. The contour integral about the rectangle of f is 0. So the way to think about this is that how things go wrong in f at z1 can basically be gotten rid of by this z minus z1 multiplier, right? Like if z minus z1 was in the bottom, this is kind of like multiplying it by something that'll cancel it out. Not exactly the right way to think about it, but close enough. You can sort of remove that issue, right, for a little bit. All right. So the proof is actually pretty straightforward and great. If z1 is outside of R, then the situation is just Cauchy's theorem for a rectangle. That's suppose z1's out here, then you could have just taken your region to not include it, right? And you could have just pretended you didn't have this little chunk over here. Okay, so let's, without loss of generality, let's suppose that z1 is in the interior of R. Okay, so what we'll do is we'll say, well, for epsilon greater than 0, there's a number delta greater than 0, so that, well, f of z is less than, or z minus z1, f of z, this piece right here is less than epsilon whenever z minus z1 is less than delta. Why does this happen? Well, because we're supposing that this limit is equal to 0, so of course this thing in modulus has to get close to 0 when you put in z's that are close to z1. Well, if this thing in modulus gets close to 0, then you can split that modulus up across the multiplication right there and get this little bound. All right. So if you choose delta small enough to do this, so that the square s of side length delta centered at z1, which let me make this a little bit clearer. You've got z1 right here, right in the middle, and you've got your square s of side length delta is entirely within R. Then everywhere along S, that is along all these outsides, we have that f of z in modulus is less than epsilon divided by z minus z1. That's immediately obvious from this line right here. Just divide by z minus z1 in modulus. Okay, so we can form 9 subrectangles by extending the sides of S, just as shown in this figure. Okay, and by Cauchy's theorem for a rectangle, the integrals of f around all 8 of the subrectangles other than S are 0, right? So as you start to go around this piece, you're going to get 0, and 0, and 0, and 0, right? Just again and again and again. So as you go around each of them, you get 0. So you could add all of it up. And notice, if you add it all up, all of it goes away except for this one right there. Okay, this is the one that matters, integrating around this middle rectangle. This is kind of like what we did in the deformation theorem, right? Where we, you can imagine you like went in along here and then, went like along a piece, right? That kind of business. So, the integral around S of f is equal to the integral about R of f. But along S, notice, the modulus of f of z is less than epsilon over z minus z1. We know that already from up here, right? So this is just this statement right here because we've chosen delta to be small enough. And now, notice that z minus z1, that's less than delta over 2. Why is this? Well, because the closest you can be to z1 for something on this path S, this square, is, well, delta over 2. That's this length right here. That's delta over 2. That's the closest you can be. So if the closest distance you can be is delta over 2, then when you take the reciprocal, that is bigger, right? Okay, so then just do a little bit of arithmetic. 2 epsilon over delta, bada boom, right? So if this thing is bigger than delta over 2, right, then when you divide by it, you get something smaller, if that wasn't clear. And you get 2 epsilon over delta at the end of it. So f of z is bounded by 2 epsilon over delta. Okay. Then, notice, we've got an upper bound for the modulus of f, and we'll use that upper bound theorem again. So when we take the contour integral about S of f, the modulus of this guy, of course, we can just say that that's the length of S times this upper bound for f, which is 2 epsilon over delta. What's the length of S? Well, S is the square of side length delta, so it's just the perimeter. That's 4 delta. 4 delta, 2 epsilon, those deltas cancel out. We just get 8 epsilon. So 8 times something that's as small as you want, you can still make it as small as you want, right? So if this holds for every epsilon greater than 0, if you can make it as small as you want, then you must have 0 in modulus, and that means that the contour integral around R of f is 0 as desired. Okay, bada boom, that's kind of a smooth proof. So kind of the same business once again, just dividing things up into little chunks, getting upper bounds, using that bounding theorem. This is one of the most classic tricks from analysis, is to get upper bounds for things, show that you can make those upper bounds small, and show that that gives you 0. All right. Is my cat scratching something? Sorry, my cat is scratching something, and my son is crying. It sounds like we're having a bit of a shit show in the Christofferson household tonight. All right. So if we want to, we can go a little bit further as well, and we can actually strengthen the assumptions on f, and then deal with the case where maybe this point where things go bad and you don't have analyticity is actually on that boundary. So if you take a little bit stronger of a condition, and at least suppose that f is continuous at z1, then it's fine if z1 is on the path. And this is the content of lemma 2.3.4. So we're going to once again suppose that R is a rectangular path with sides parallel to the axes, and that f is a function defined and continuous on an open set G containing R in its interior. So far, these are just Cauchy's theorem for a rectangle again. And now, here's the difference. Like I said, f is analytic on G, except at some fixed point z1 in G. All right, fair enough. Then the integral of f about R is 0. Okay, so the idea here is very similar but slightly different, and so it's kind of fun to see the differences. We'll let epsilon be greater than 0, be arbitrary. Then we can choose a delta so that f of z minus z1 is less than epsilon whenever z minus z1 is less than delta. This is just continuity, right? Okay, so, just as you approach z1, you get close to the value of f of z1, right? Close, nearby inputs, nearby outputs, that whole business of continuity. Okay, so up to adding a constant to f, let's just assume that f of z1 is equal to 0. That is, if f of z1 wasn't equal to 0, we could replace f with something like, like f tilde of z is f of z minus f of z1, right? And we've just moved things up or down, left or right, in the complex plane. We've just moved it over. Nothing else has changed. So we can just assume that that's the case, since we could just replace it, and it would just be more annoying to write down, but it wouldn't actually change anything. So let's just assume that. All right, so if z1's not on R, then our previous lemma applies, and we could just use that. If it is on R, then what we'll do is we'll let S be a square of side delta, half a square of side delta, and we'll subdivide R as shown in this figure. So since it might be kind of hard to see, we've got S. It's got a side of length delta and a side of length delta over 2. And I've got z1 right there on the edge of S. God, that is a horrible S I drew. I'm sorry. There we go. All right. So we've just done this, and we will break apart R into 1, 2, 3, 4, 5, 6 rectangles, and about all of these other ones. When we go around all the other guys, we get 0, 0, and you can kind of see the exact same thing happening all over again. We go about all these other guys, we get 0, and so hey, when I integrate around R, I get the same thing as when I integrate around S. So the integral about S of f is the same as the integral about R of f. So along S, though, we have that f of z is less than epsilon in modulus. Why is this? Well, we've supposed that f of z1 is 0, so if f of z minus f of z1 is less than epsilon, whenever these guys are within a delta, right? Which, hey, if you are on this little box right here, if you're on the other side, then you are delta over 2 away. And so if you're up here, that's the farthest away you could be. You've got a side of delta over 2 and a side of delta over 2. And so the distance here is less than delta. Just, do a little bit of Pythagorean theorem. And so this is still less than epsilon, right? Since these guys are less than delta. Okay. So f of z is less than epsilon. Thus, if delta is less than 1/3, since, we just have some delta, if it's at least less than 1/3, if it's not, you could always choose a delta that's smaller, since choosing an even smaller delta won't make this bigger, right? Then notice if you add up the perimeter, you'll have a delta over 2, a delta over 2, a delta, and a delta. So 2 delta plus 2 times delta over 2, that's 3 delta. Hey, how about that? So if delta is less than 1/3, then the length of S is 3 delta, and we'll get 3 delta epsilon less than epsilon, right? All right, kind of cool. Therefore, if we have this nice modulus here of f about r, that's the same as the modulus of the integral about s of f, and that's less than epsilon for every epsilon greater than 0, 3 delta epsilon. If delta is less than 1/3, then this is just less than epsilon. So this thing, if we can make it as small as we want, if it's smaller than an arbitrary positive number, then you can make that as small as you like. And so in modulus is 0. The only thing that has 0 modulus is 0 itself. So the contour integral about r of f is 0, just like we hoped for. How about that? Kind of a mouthful, but it is pretty similar to the other proofs. Once again, we're just splitting things into smaller rectangles. Gorsot's method of repeated bisection, a nice trick. And we can, of course, do similar things and strengthen Cauchy's theorem for a disk. We obtain the corresponding conclusions, of course. So if you strengthen Cauchy's theorem for a disk, the conclusions for that one hold if we assume only that the function f is continuous on D and analytic on D sans Z1 for some Z1 in D. So, all right, cool. Not too bad. That works out okay. The fun thing we're going to do next, now that we've got Cauchy's theorem for a disk and Cauchy's theorem for a rectangle, is we're going to start talking about homotopies. And we'll do this in a little bit more formal of a way than our hand-waving, oh, can you deform the curve? You know, think about our rubber band, can it fit a certain shape and blah, 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 right? Can you bend it, right? We'll go away from that into a more formal definition of homotopy. We'll talk a little bit about simply connected regions in this more formal way, and we'll build ourselves back up to the deformation theorem. And since we've got Cauchy's theorem for rectangles that allowed us to get Cauchy's theorem for disks, then if you can deform something into a disk or something like a rectangle, which notice is just like a series of pieces hooked together at non-differentiable angles and stuff, you will be able to get the deformation theorem in the nice fancy way. So we will talk about that next time and a little bit more. We will finish out 2.3, do some more wonderful kind of confusing proofs. If you're not used to them, at least, then maybe they're confusing. If you are used to them and you've seen these kind of things before, then this is probably old hat. But if it's your first time around, don't feel bad if all the epsilon delta arguments seem like Greek at first. You'll get used to it. We'll do a lot more of those next time, and you have a great opportunity for extra credit writing up a proof that is in your textbook, so there's really no reason not to do it. I think that's all I got for you today. The key for your last homework is online if you want to see that, and if you have any questions about changes to the schedule, let me know. I'll see you on Friday. Awesome.